Welcome again. In this video, I will redefine good and bad parts for smooth control. We will demonstrate the need. We will demonstrate that our old definition introduces oscillations. We will study that through the DC motor control problem. We will present the Scilab code and results. So let us look at the control of DC motor problem presented by Astrom and Wittenmark. x1 is the velocity of motor shaft, x2 is the position. Here is the state space equation. The requirements for a step response are rise time should be 3 seconds, overshoot of not more than 5%. He chose TS as 0.25 second. They chose TS as 0.25 second. We will use the same value. We obtain the following transfer function. So here is the discrete time transfer function we obtained in the previous slide. We can factor the good and bad parts of the denominator. You can verify that these are good and bad factors, and the denominator already has a delta. As a result, an integral mode is not required in the controller. The plant itself has it. Here is the factorization of B. Everything is good here. In fact, you can see that the 0 of BG is inside the unit circle. I want you to write this down, so I have written it in blue. We are going to discuss this in the subsequent slide. So here is the characteristic polynomial for the step response requirement. When I solve Aryabhata's identity, I get this R1 and S1. When I simulate with this controller, I get lot of oscillations. Plant output is on the left hand side. It is fairly smooth, but the control effort changes rapidly, and this cannot be implemented in reality. It will result in wear and tear of the control valve. Now we will explain why the control effort is oscillatory. Recall this controller. This is our standard 2-DOF controller, and recall how we defined RC earlier. RC was given as BG R1. Similarly, we had for TC and SC. The important thing to notice is the denominator here, where we have this BG. The cancelled part shows up in the controller. We cancelled BG, it shows up in the controller. Remember, BG was this, and this has a 0 at this point, which is minus 0.9201. What is important to remember is the minus sign. Although this is inside the unit circle, it has a minus value. This is going to be important. You have to remember this when we discuss this further in the next few slides. So BG has a root at minus 0.9201, which is a negative value. This causes oscillations. Why? Recall what happens when we have poles on the negative real axis. They introduce oscillations. Our controller has a pole at minus 0.9201. The way we have taken our good B, and hence the control effort is oscillatory. Okay, we have this BG appearing here. This is the troublemaker, so we need to get rid of this. How do we get rid of this? Anything we call as good shows up in the denominator in the controller. So if you don't want something to show up, call it bad. Bad does not show up. So to prevent a factor from showing up, define it as bad. the easiest thing to do is to define factors with negative real parts as bad. A better solution is bad factors should lie outside shaded region of the desired region analysis. What we will do now is we will define factors with negative real parts as bad. Let us recalculate. No change in the way we factored A. We will redefine BB and BG. Let B include negative zeros. So what was called as good before is now taken as bad. Phi is the same as before. Now when we solve the Aryabhata's identity with the new factorization, we get R1 and S1 as given here. Here is the Scilab code that I used, motor.sce. It uses this function pp underscore im, and here is pp underscore im.sci. It uses a new polynomial split algorithm, pol split 3, and then xd, y and c is called to solve the Aryabhata's identity and so on. Here is pol split 3.sci. I would suggest you go through this later. After designing the controller, we invoke this file motor underscore param.sce. It loads this xcos code and sets the limits for plots and simulates. It simulates automatically. Remember, you have to make sure that you specify the complete path for this xcos diagram, both here and also here. When I do this, okay, before that, here is the screenshot of the xcos diagram. This controller results in a very well behaved control effort U. The oscillations that we had have been completely removed. The corresponding output is given here. It is more or less the same as what we had obtained earlier. There is no loss of information. This output is not in any way inferior to the previous output. In other words, we got the same output and the control effort improved significantly, and in fact the control effort is something that we can implement. There are no oscillations and hence there are no wear and tear of the control valve. Of course, the rise time is not as we wanted. If we want to shorten the rise time, we may want to change the specs from 3 to 2 seconds. With this, we have come to the end of this presentation. From now on, this is how we will define good and bad factors. I would want you to reproduce the results. I am making available all the Scilab code. Please try them out. Thanks for joining. Goodbye.